Okay, so we have some additional facts about polynomials. The first is a statement. Go ahead and write it down and then we'll explain it. A polynomial of degree n has exactly n zeros in the complex number system. So hopefully you recall that when we were first finding roots, we were only paying attention to the real roots. We didn't even deal with the imaginary ones. And we had a statement that said, if a polynomial has degree n, then it has at most n real roots. Well, that statement is still true. This statement is not contradicting that. But now that we know about complex roots, if we add in the imaginary ones, then there's going to be exactly n roots. So the first thing, I want you to make sure that you understand that real numbers are in the complex number system. So let's say I have the number 5. That's a real number. We can plot the number 5 on the number line. But I can express the number 5 as 5 plus 0i, and that is now a complex number in standard form. So do you see that it doesn't have to be a 5, but any real number can be written as a complex number? So when we think about the complex numbers, it's not like real numbers are here by my index finger and complex numbers are over here by my pinky finger and they're separate. No. The real numbers are a subset of the complex number system. So it's like we have all the real numbers, all the numbers that can go on a number line, and our real numbers can be both rational or irrational. And then the complex number system adds in the imaginaries, but the real numbers are a subset. They're still part of it. All right, so let's take a look at a problem and how this information is put to use. So let's say I have the polynomial x to the 4th plus 21x squared minus 100. So if I use the fact above and I say, well, what is the degree of this polynomial? What is the degree? 4, right? The degree is the highest exponent. So my degree is 4. So exactly how many zeros am I going to have?
4.
It's going to be 4 zeros. So we know one way that we can identify zeros is we can type this into our calculator and we can look for the zeros in the table. And if we do that, we're not going to take the time to do that, but if we did, I'll just tell you this, you'd only find 2. So this statement right here would let you know that there's 2 other ones that you would need to find. Like you don't just find 2 and be done. There's 2 others. Alright, so we're going to go ahead and factor this. Now it is a quartic, that means that's 4th degree, but we're going to follow the pattern that we would use for a quadratic. Because you see you have x to the 4th, but do you see there's no x cubed and there's no x? So this looks a lot like an x squared plus 21x minus 100. Except I've got x to the 4th and x squared. So we're going to follow the pattern of quadratics. So I'm going to set up my 2 parentheses. And instead of saying x times x, I'm going to say x squared times x squared. Because x squared times x squared would make x to the 4th. And then do you see then that your middle terms are both going to have an x squared in them? So now we just need to determine what can multiply together to make negative 100 that would add together and make positive 21. Think about that, and when you know, raise your hand. All right, I see 2 hands. 3, 4, 6, 7. All right, Lance, what do you have?
Negative 25, 4. Oh, other way around.
What do you mean by that?
So, minus 25, and then plus 4.
All right, I'm going to need 1 minus and 1 plus. I agree that the numbers are 25 and 4.
Negative 4 and 25.
We need to get a positive on the 21, right? So that needs to be the higher number. So negative 4 and positive 25. Do we all agree that that works? Negative 4 times 25 gives us negative 100. We got negative 4x squared and positive 25x squared. All right, so if I'm finding zeros, I'm wanting to know when does this polynomial equal 0? When is my output equal to 0? So what do I do at this point? I'm going to set each factor equal to 0. So if I solve my first equation, I'd have x squared is equal to 4. I'd take the square root of both sides, plus or minus. And so x would be plus or minus 2. So I've got x equals 2. I've got x equals negative 2. Those are real numbers. I would see those answers in my table. 2, 0, negative 2, 0. From my other equation, I'm going to subtract 25 from both sides. And I've got x squared is equal to negative 25. I'm going to take the square root of both sides, plus or minus. X is going to be plus or minus 5i. So I'm going to have a 0 at positive 5i, and I'm going to have a 0 at negative 5i. And so there are my 4 zeros. But you're not going to find the 5i and the negative 5i by looking at your table. Right? So this statement up here lets you know that there are 4 zeros to be found. These two imaginary ones are only going to be found algebraically. Right? When you look on your graph, you're going to see an x-intercept at negative 2 and an x-intercept at positive 2, but there's not going to be any other x-intercepts because your other zeros are imaginary. Right? Okay, we have one more statement to add, and that is if a complex number is a 0, then its complex conjugate is also a 0. So that is just something that is always going to be true, and it's helpful, and lets us know that our imaginary zeros are always going to occur in pairs. So for this problem above, I have the number 0 plus 5i, right? That's what 5i would look like in standard form. And so the conjugate would be 0 minus 5i. And so do you see that both 5i and negative 5i are both zeros? And that's what that statement is meaning. So that helps you with your imaginary roots.